Hello and welcome again to my Physical Science online video supplement series. Today's video is another of my lab supplement videos. I'm going to make use of the Colorado simulation, the Colorado Physics Education Team's simulation of concentration, because today's video is the concentration lab discussion and examples walkthrough video. So let's go ahead and pull up the lab instruction. We're looking at our solubility lab, and there are in fact actually two different simulations that you can make use of. A word of caution here, a couple words of caution. The simulation is not exactly like the lab that you're going to be doing. Here are a couple of differences. First of all, in the lab that you're doing, you want to measure the concentration as a function of the temperature of the water. Second of all, you're measuring everything in units of grams of the solute dissolved per basically kilogram of the water that you're using. And so if you look down here, you can see actually to follow our textbook, we're going to use in terms of 100 grams worth of water per how many gram of whatever's being dissolved. So your units have what seems like a funny unit for solubility. It's basically number of grams solute per 100 grams of water. So with that said, let's go ahead and launch one of the simulations. This is the concentration simulation. There's actually a second one on here that's specific to sugar and salt, but I'm going to go ahead and do the concentration simulation because it's, despite the fact that it's using different materials than what you're supposed to be using, it's actually a little bit closer to the lab that we're doing. So here is what the interface for this simulation looks like. You can choose what you're going to use as your solute. I'm going to stick with potassium dichromate. Now, one of those differences that I mentioned between this simulation and your lab is that you'll notice this gives concentration in moles per liter. So this is how many moles of this potassium dichromate are dissolved per liter of water. So to make it more consistent with the lab, what we would have to do is look up what the molar mass of potassium dichromate is. The answer is about 294.185 grams per mole. Alright, so whatever this number is, the moles per liter, we have to multiply first by 294-ish to get this into grams of potassium dichromate per mole, liter, of water. And then to boot, 1 liter of water has a mass of 1 kilogram. So if we want to convert everything into grams per 100 grams, we would have to convert the kilograms into increments of 100 grams. So there's 1,000 grams per kilogram, so we're going to be doing a little more multiplying. So I'll work an example with that, but first let's go ahead and dump a little bit of this potassium dichromate into the water. So you see I've set it so there's a half a liter of water. I can actually only have up to about a liter in here. In your experiment, you're supposed to use 2 liters. The other difference between the simulation and your experiment is that, as far as I can tell, there's no way to actually change the temperature of the water. So that's kind of unfortunate. That actually might be a thing that they could try to improve in the future. But if you look at your textbook, you can see the curves that show the temperature dependence of the solubility of these different solutes, and they're not trivial curves to duplicate. So I will say from the standpoint of would this be easy to incorporate in this program, it's not going to be trivial it may or may not be very hard to incorporate, but for the purpose of this video, I suppose it's okay that that's not there. So let's see, how do we add a little bit of this potassium dichromate? Well, you shake the container and out comes the potassium dichromate. What you're supposed to do in the lab is add this stuff a little bit at a time. So I've actually added quite a bit already, a lot more than you should be adding, because if I do a little bit of a shake, this is 0.035 moles, 0.435, excuse me, one shake, and I've just added 0.035 moles more. So we can do a quick calculation. I added 0.035 moles and the mass is 294 grams per mole. That means that I just added 10 grams of potassium dichromate to the water by this small amount of shaking. So what you're supposed to do is basically be adding some of this, and we're saturated. So it's saturated. You can in fact see some little crystals of potassium dichromate at the bottom of the water. You will see this if you saturate with salt or with sugar, and of course if I add some more, it's just going to be more crystals collecting at the bottom, and I'm not adding any concentration here because all of the crystals I'm adding sort of fall out at the bottom. They condense at the bottom, if you will, or they congregate at the bottom. So this means basically that I have reached my saturation limit. In the simulation, I can just look and see what the concentration is, and it's 0.510 moles per liter. So let's pull up our workspace, and we have saturation at 0.510 moles per liter of water. Alright, so that's the same as 0.510 moles per kilogram of water. So we need to convert the kilograms into 100 gram increments. We need to convert the moles to a mass. So 0.510 moles times 294.185 grams per mole is going to convert this top part. And then we're dividing by 1 kilogram times 1,000 grams per kilogram, and then from there we need to divide out by increments of 100 because we want to have per 100 gram. So that's why we are dividing this by 100. So this basically means that we're going to end up dividing by 10 ultimately, because you can see we can cancel out 100 with the first two zeros of 1,000. And so this gives us the per 100 gram increments. Top part, what we do is we just multiply the 510, the 0.510 times the molar mass, which was 294.185. So you're left with this, divide by 10, and what you get is that the concentration for saturation, I'll call it C-sat, is 15.0 grams of potassium dichromate. So potassium dichromate per 100 grams of water. So that's the form that we're looking for in this lab. And again, the reason why I'm having you put things in this form as opposed to moles per liter or even grams per liter This is probably a more convenient looking unit. However, I'm having you do it this way because if you open up your textbook, you will see that if we look under the chapter for the chemical elements, that you can find a chart in here that has to do with the solubility, and it should be on page 308. And if you look at this chart, it lists solubility in grams solute per 100 grams of water as a function of temperature. So you'll notice that sugar is in fact one of the things that is on this chart. So part of this lab that you're doing is actually to duplicate this curve for sugar. You're raising the water temperature. Maybe you can only go up to 65 degrees on this chart. So you can in fact raise the temperature more if you want and see what this curve looks like beyond this highest temperature that we see on this particular chart. You'll notice that salt is not one of the things that's on this chart. So you're kind of producing a new curve after having produced this one. So do sugar first as a confidence builder. Make sure that you get something that looks like this. Then you can do salt. This leaves me with a few brief loose ends that we can tie together for this lab. First of all, there's a question about what happens after you've dissolved the sugar at 60 degrees until you reach saturation. So just before reaching saturation, and then you allow the water to cool. Just do this and see what happens. I'm not going to give you the answer here. Then another loose end here is that we can do for practice a calculation similar to the type that we would have on this table. And then finally, the next loose end is that you're supposed to calculate the expected solubility of salt. Compare the actual value you get at 25 degrees C to the value that's expected of 360 grams. So let's try these two loose ends in turn. So for our first example, let's say that you dissolve 700 grams of salt in 2 liters of water at 25 degrees C before saturating. So the question is, what is the saturation concentration in both units of grams salt per kilogram water and in units of grams salt per 100 grams of water? Okay, so to answer this, we use CSAT, that's the saturation concentration, CSAT, is equal to, we had 700 grams of salt per 2.0 liters of water. All right, and we have to basically convert this into kilograms of water. So the density of water, recall, is 1.00 kilogram per liter, or if you would like, it's 1 gram per milliliter. So we multiply these things together, we divide by the 2, and what you end up with is 350 grams of salt per 1.00 kilogram of water. Alright, and in fact, if we're keeping track of significant figures, we should probably call this per 1.0 kilogram of water. So that answers part A. Part B, CSAT, is also equal to 350 grams of salt per 1.0 kilogram of water times, basically you can write 10 of 100 grams per 1 kilogram. And this is because there's 1,000 grams in 1 kilogram, and we basically want to break it up not in chunks of grams, but in chunks of basically of 100 gram increments. So this right here ends up looking like 35 grams of salt per 100 grams of water. So that's what our saturation concentration is, both in units for A and units for B. So this brings me to the second example, which is really part 2 of this first example, which is what is the percent error for the measured value that we had here, 350 grams per kilogram, as compared to the expected or theoretical value of the saturation solubility. So I'm pulling up this last page of your lab instructions, and it says the expected solubility of salt is 360 grams per kilogram of water at 25 degrees C. So this is the number we're actually comparing to. So recall that to get the percent error, you basically want to compare the experiment to the theory by subtracting the two from each other, taking an absolute value, and then dividing by, depending on which one you want to compare to which, you divide by either the experiment or the theory. I like to compare the theory to the experiment, but a lot of other people will disagree and say no, it's more important to compare experiment to theory. So this is the method that I usually use, including on your Blackboard quizzes, so do it in this order. And so what this looks like is the absolute value of 350 grams salt per per 1 kilogram water minus 360 grams salt per 1 kilogram water, all with an absolute value, and then divided by the experiment, which was 350 grams salt per 1.0 kilogram water. Notice, by the way, that all the units here cancel, and so you're left with percent error is equal to basically 350 minus 360 divided by 350. So this, of course, this top one is negative 10. You take an absolute value, you end up with 10. So it's 10 divided by 350. And actually we need to convert it to a percent, we need to now multiply by 100%. And so you end up with a percent error of 2.8. So really I should also have a times 100% in here. Times 100%. And then times 100%. And so this is 2.857. So we'll call it 2.9% error. Okay, one last thing to calculate here, which is that, so we now have a experimental value basically for how much salt was dissolved in the water at 25 degrees C. So how do you get for 30 degrees C? Well, you basically add a little bit of salt at a time in 5 grams or 10 gram increments until you reach a saturation value here. So then you have to keep track of how much you added and how much you had here. And so let's say that you add another, let's say 30 grams of salt before you reach saturation here. Well, you can just add this 30 grams to the 350 grams that you found here, or the, as the case may be, the 700 grams you found here. And so what you'd end up with is that at 30 degrees C, have 30 grams plus 700 grams, which is 730 grams, dissolved in 2.0 liters of water. So again, You can do the conversion for this. It's the same as the one we did above. It's basically 730 grams per 2.0 liters, which is the same thing as 365 grams per 1 kilogram. This is salt, and this is water. Salt and water. And so that's also 36.5 grams of salt per 100 grams of water. So if you are really careful, you may be able to finish out most of this table in one fell swoop by doing that process. If you're not careful, if you put too much salt in and it instantly saturates, it means you're going to have to start all over again. So dump out your salt water, add in 2 liters of really fresh water, maybe even rinse out the pot that you're putting this in first to make sure that any residual salt is removed. Add your 2 liters of water, then start from scratch. Add in, maybe you can add up to 350 grams because you know that that's what's in the 25, and then add a smaller increment than before to the 30 until you reach the saturation. Okay, so I think that's all that you need to do this particular lab. This is hopefully a helpful video for you, and thanks for watching.